Alright guys, now that you have drawn the cross-section and represented all the moments and all the forces acting on the cross-section, you can proceed by calculating the normal and the shear force at any point of your choice. Now, the question asked us to calculate the normal and the shear stresses at points A and B, where A belongs to the z-axis in here and B belongs to the x-axis. Right? This is the x-axis. All right. Now, how do you proceed? Step 5. I always recommend you find the cross-sectional properties. You find the cross-sectional properties in step 5 because you're gonna use them later on. So find the cross-sectional properties. And how do you do that? Well, the cross-sectional properties, first the centroid. Since this is a full disk of radius 5 millimeters, the centroid is located at the middle, so there is no need to find x bar and y bar. We know that the centroid is located at the middle. We know that x bar is 5 millimeters and z bar is 5 millimeters. So centroid x bar equals z bar equals 5 millimeters, right? Because it's located at the middle. Remember, the disk has a diameter of 10 millimeters. Now the moment of inertia, which we're gonna use in bending stresses. Now, since this is circular, Ix is equal to Iz, alright? It's equal to pi over 4 multiplied by the radius, which is 5 to the power 4, right? And it's going to be equal to 490.87 millimeter to the power 4. Now, what about the polar moment of inertia? The polar moment of inertia, it is J, which is equal to 2 multiplied by I, and it's equal to 2 times 490.87, and it is equal to 981.75, right? Actually 0.74, so 981.74 millimeter to the power 4. Okay, perfect. We have also the area, which is pi r squared, so it's equal to pi times r, which is 5 squared. This is the area of the cross section, which is 78.54. So this is 78.54 millimeters squared. Okay, so we got the moment of inertia, we got the polar moment of inertia, and we got the area. Okay, so let's start. So step 6, after we get the cross-sectional properties, let's start by finding the normal stress at point A. So here, this is an I. Okay, this is an I. So in step 6, find the normal force. Find the normal stress at point A. Okay. Now always remember that sigma A is equal to the sigma due to the force plus sigma due to the bending. Okay, very important, very important. How do we find sigma due to the force? Is there any normal force acting on the cross-section that is creating normal stress? Of course there is. It is the weight that is acting into the page, and it is acting in compression. Because recall, normal forces are forces that are perpendicular to the area of interest. And what is the area of interest in this case? It is the area of the cross-section. And notice that W, which is the weight, is acting in a way that is perpendicular to the cross-section. So W is causing a compressive force, and therefore it's going to be minus W over A. Okay? The effect of the force is uniform, and it's equal to the force over the area. Okay. Now here we have double bending. We have the bending about the z-axis, and we have bending about the x-axis. Is there any bending stress at point A due to mz? Okay. So I'm going to put in here plus or minus mz x over iz plus or minus mx z over I x. Is there any bending stress due to mz? I mean, what is this term? Is this term equal to 0? Let's go and see. Since point A lies on the z-axis, then the bending moment about the z-axis doesn't cause any normal stress, any bending stress at point A. Why? Because recall, in the bending stresses, x in here is what? X in here, since x is vertical, since the x-axis is now vertical, x in here is the vertical distance between the point A and the horizontal centroidal axis. Okay, so if I tell you mzx over iz, since x is vertical, it's going to be the vertical distance between point A and the horizontal centroidal axis. But the horizontal centroidal axis is z, so there is no vertical distance. Between z and point A. Point A lies on z, so x is 0, and therefore mz is equal to 0. In fact, I'll give you a trick. Whenever the point lies on the axis that is a subscript of the moment, then there is no bending stress due to that moment. Okay, so I'm going to put it in here. Since point A lies on the z-axis, this means that mzx over iz is equal to 0. Okay, since the point lies on the z-axis, there is no bending due to mz. So I'm going to put it in. There is no bending stress due to mz. Alright, now so this thing is gonna go to 0. Now what about mx? So is it gonna be plus or minus? Now notice in here that when we're dealing with mx z over ix, z is the horizontal distance between the point of interest and the vertical neutral axis, right? So I'm gonna write this down. So let us be clear in here. So this is minus w over a plus or minus mx z over ix, and z in here is going to be the horizontal distance, because z is the horizontal axis. It's going to be the horizontal distance between a and the vertical centroidal axis, which is what? Which is the x-axis. So it's going to be the horizontal distance between A and the x-axis, meaning x in here is going to be 5 millimeters. Perfect. Now all I need to do is to decide whether the mxz over ix is plus or minus. I know there is a lot of stuff in here, but we're going to solve a lot of examples, so this thing becomes very easy for you. So how do I know whether A is under a plus or minus due to mx? I want to see if A is in the tension zone or in the compression zone due to mx. So look at the figure and tell me, due to mx, is A in the tension or the compression zone? Of course it is in the tension zone. Why? Because notice in here that mx has this as a tension zone and this is at the compression zone. Why? Because the arrow in here is for compression. Okay, so we now know that A is under the tension zone with respect to mx, and therefore this would be a plus. Why? Because A is under tension due to mx, and therefore sigma at point A is minus w over A plus mx z over ix. What's w? W is 100 kilonewtons, so minus 100 multiplied by 10 to the power 3 to change it to newtons, over the area, which we calculated in step 5, it is equal to 78.54, plus mx is given in kilonewton meter, we have to change it to newton millimeters, so plus 300.5 multiplied by 10 to the power 3, sorry, 10 to the power 6 to change it to newton millimeter, multiplied by z, which is 5 millimeters, over ix, which we calculated earlier to be 490.87. So you're gonna get in here 3059619, 3 million megapascal. It's insane. You're not gonna get such a thing. You're not gonna get such a thing. All right. If you want to change it to gigapascal, it would be 3060 gigapascal. It's insane. Don't expect this very much high number. Why? Because the stresses are very huge and the cross section is very small. This is not acceptable. Alright, so from gigapascal to megapascal, we multiply it by 10 to the power 3. Okay, so I just divided by 10 to the power 3. It's 3060 gigapascal. Okay, so this is the normal stress at point A. Since it turned out to be positive, alright, this is going to be in tension because the stress turned out to be positive. So since sigma A is positive, this means A is under tension. Perfect. This is how to calculate sigma at point A. This is it. This is it. Now, let's continue to find the shear. So, step number 7, let's find the shear at point A. Okay, so again, to find the normal stress at point A, we consider the effect of the force and the effect of the bending moment. Since A belongs to the z-axis, there is no effect on point A due to mz. Okay, and because W acts in compression, this means that sigma force is going to be minus P over A, and A is under the tension zone due to mx. Okay, and it's going to be in the tension zone, and therefore it's going to be a plus mx z over ix. Okay, now what happens to the shear? How to calculate the shear stress at point A? So find the shear stress. Recall that the shear stress at a point is equal to what's happening due to the force plus what's happening due to the torsion. So let's start by tau force, and it is VQ over IT. Now, since the shear is vertical, right? Because recall in here we have only the vertical shear, which is F equals to 70 kilonewtons. Okay, so the shear is vertical, so it is VY Q over IX T. Alright, so Vy in here is equal to 70 kilonewtons. Ix is calculated to be 490.87 millimeter to the power 4. So this is 70,000 newtons. Q is A prime, Y prime, where A prime is the area, what do you say? It is the area above or below, or the right or to the left. Since the shear is vertical, A prime is going to be the area above or below the point of interest. A prime is going to be above or below the point of interest. So A prime is the area above or below point A. Let's take it to be above for the sake of this exercise. So A prime is going to be the area above point A. This is point A. It's going to be the area above point A, and it's going to be the area of a semicircle, so it's going to be pi r squared over 2. Alright, which is 39.27 millimeters squared. And what is Y prime? Y prime is going to be, sorry, it's not Y prime in this case. In this case, it is X prime, because the vertical axis is now X and not Y. So it's going to be A prime, X prime, because it's very weird now that we have the X axis to be vertical, but it's going to be A prime, X prime. Okay, so A prime multiplied by the vertical distance. X prime is going to be the vertical distance between the horizontal neutral axis, which is Z, so the horizontal neutral axis, and the centroid of A prime. The horizontal neutral axis is here. This is Z. So it's the vertical distance between the Z axis and the centroid of A prime. Where does the centroid of A prime lie? This is the centroid of a semicircle. It's at 4r over 3 pi. This is going to be your X prime. Okay? It's going to be the vertical distance between the horizontal centroidal axis and the centroid of A prime. And the centroid of A prime is the centroid of a semicircle, which is going to be 4r over 3 pi. And this means that we're going to have in here equals 39.27 multiplied by 4 times r over 3 pi. So 39.27 times 4r over 3 pi. And it's going to be 83.33 millimeter cubed. So this would be your Q. This would be your Q. Alright? Now what is T going to be equal to? T. What's T? Since we're dealing with vertical shear force, T is going to be the horizontal distance pass a horizontal line passing through point A, and get the thickness. The thickness is going to be 10 millimeters because it's going to be equal to the diameter, right? So it's going to be equal to, this is going to be equal to, T is going to be equal to 10, right? So T is going to be equal to 10 millimeters, and so we can find out that tau due to the force is V, which is 70 multiplied by 10 to the power 3, change it to newtons, times Q, which is equal to 83.33, over I, which is equal to 490.87, multiplied by T, which is 10, and this would be equal to, so it's going to be 1188 megapascal. It's not sufficient to find the magnitude, we have to find the direction of the shear stress also. It's going to be important later. So the direction of the shear stress follows the same direction as the shear force, remember, right? So when I put this as a remark, direction of shear stress is the same as that of the shear force, all right, and it's going to be upwards. But this is not it. We're not done yet. We're not done yet. We still have the effect of the torsion. Okay, but let's recall what we did for the force. So for the force, it's VQ over IT. The shear is vertical, and since the shear is vertical, Q is going to be A prime X prime in this case, where A prime is the area above or below the point of interest, and X prime, in this case since X is vertical, is going to be the vertical distance between the centroid of A prime and the horizontal neutral axis. I is going to be the moment of inertia about the horizontal axis, but in this case Ix is equal to Iy since the section is circular. And T is going to be the horizontal thickness because the shear is vertical. It's going to be the horizontal distance that of the solid line passing through point A horizontally. Now tau due to the torsion is equal to Tc or T rho over J. T, which is the torsion, we know the direction of the torsion, which is we know the magnitude of the torsion, which is equal to 210.35, kind of big, very big, 210.35. So in here it's going to be 210.35 multiplied by 10 to the power 6, again from kilonewton meter to newton millimeter, multiplied by rho, which is the radial distance between the center and point A, which is equal to 5, the radius, over J, which is equal to 490.87 times 2, 981.74. Very simple. So we calculate this. 107, again, very weird numbers, 107.1312 megapascal. 1 million megapascal, very, very large, not acceptable, my bad, I chose the wrong numbers, right? So, however, of course, I'm giving you the step-by-step procedure. We're going to solve examples from the book later on. So, tau torsion is 1,071,312 megapascal, all right? How do we know the direction of the shear stress at point A due to torsion? Recall, the direction of the shear stress at a point due to torsion follows the direction of the torsion and is at the same time perpendicular to the radius. Okay, since the torsion is acting in a clockwise fashion, then this would be the direction of the shear stress due to torsion at point A, okay, directed downwards. All right, so recall in here, I'm going to put this as a remark also. Put this as a remark. So the direction of the shear stress due to torsion follows that of the torsion and is perpendicular to the radius. Recall that from chapter 5. And so it's going to be downwards. So you have 1188 megapascal acting upwards due to shear force, 1,071,312 megapascal acting downwards due to torsion, and therefore you can get now the net shear stress. So therefore tau at point A is going to be 1,071,312 minus 1188, right? So 107 1312 minus 1188, you're going to get a 107 0124. Again, very huge number. You're not going to get such numbers. So megapascal acting downwards. Okay, acting downwards. Why is it acting downwards? Because looking at these two, of course the downwards direction won. The downwards direction won. Okay, because the torsion is greater. Okay, so one is acting upward, one is acting downward. I subtract them from each other. The downward direction. We're not gonna always subtract them from each other. Depending on if they are both upwards, then you're gonna add them to each other. Do you get me? So it depends on both directions, the shear and the moment. This thing is in here is J. Okay. So these are the steps that you should follow to find out the normal and the shear stress at any point at A or B. Okay. I think I'm done with this video. In the next video, I'm gonna continue finding. I'm gonna continue to find out. Sorry, the normal and the shear stress at point B. But we're gonna follow the same steps. So we start by the normal stress at point A is equal to the normal stress due to the force plus the normal force due to the bending. And here we have a compressive force. This means we have a compressive stress minus W over A. Point A lies on the Z axis. This means there is no effect with respect to MZ. Point A lies in the tension zone of the X axis, of MX, sorry. So it's going to be plus MXI over Z, over IX, plus MXZ over IX. The shear at point A, stress at point A, is going to be equal to the shear stress due to the force plus the shear stress due to the torsion. The shear stress due to the force is going to be equal to VQ over IT. Since the shear force is vertical, then it's going to be equal to V, which is the shear force, multiplied by Q, which is going to be A prime X prime. A prime is the area above or below point A, which is the area of a semicircle. And X prime is the distance between the centroid, vertical distance between the centroid of area prime and the horizontal centroidal axis. It's going to be 4r over 3 pi because the centroid of a semicircle is located 4r over 3 pi from the diameter. The shear stress due to the torsion is going to be equal to T rho over J. J is the polar moment of inertia, which is 2 times I. T is the torsion, applied torsion, which we found it to be 210.35 kilonewton meter. And rho is the radial distance between the center of the cross section and point A, which is going to be in this case 5 millimeters. Follow these steps, you get the answer. Alright? It's very important to know how to represent the moments and the forces of the cross section. Because if the representation is wrong, everything is going to be wrong. So in the next video, we're going to continue to find out the shear stress and the normal stress at point B. If you have any questions on this video, please let me know. And I'll see you soon.